Good morning, everyone. It's really a great pleasure for me to be here to give this talk about predicting catastrophic landslides. Here is a global view of landslide potential, from which you can see that we are really living on a sliding Earth. In nowadays, due to rapid population growth and global urbanization plus climate change, our human habitats are suffering from increased exposure to landslide hazards across the world. One of the biggest challenges in landslide hazard mitigation is predicting whether and when a slope would catastrophically fail. By catastrophic failure, I mean a slope experiences a runaway rupture, evolving into rapid avalanches. Here I have two examples. Left one is the Mud Creek landslide in California, which catastrophically failed in 2017 after a few years of significant deformations. So it is a catastrophic landslide. The right side is a landslide in France, which has dramatically deformed for many years, but still didn't collapse. So it is a slow landslide. Imagine the massive energy involved in a catastrophic landslide. It is almost impossible, or at least not economically viable, to prevent it from happening. What we can normally do is to predict when a failure would happen and then evacuate people from the hazard zone beforehand. The current state of practice in the landslide community is usually based on the so-called Volt's law, fit into displacement monitoring data, and then come up with some velocity thresholds for emergency planning. Another method often used is the inverse velocity method, which predicts the failure time through an extrapolation of the monitoring data of inverse velocities. However, it has been found that these methods have large uncertainties in the past practice, as can be seen for the case of Prianzo landslide, where the predicted failure time by the inverse velocity method is almost 1 year after the actual failure. So, how can we better predict catastrophic landslides? My argument is that we need to better understand the physics of landslide phenomena in order to better constrain our prediction, to better constrain the predictive laws. I will elaborate what I mean in the later slides. When we talk about the prediction of extreme events like catastrophic landslides, I have to introduce two popular but contradictory concepts. The first is black swan, which is a metaphor for an event that comes as a surprise and has a major impact, but unpredictable. The other is dragon king, a double metaphor for an event that is both extremely large in size and born of unique origin. Dragon kings exhibit different properties compared to their siblings and are potentially predictable. Many extreme events in natural systems have been found to be dragon kings, ranging from volcanic eruptions and hurricanes to social unrest and epidemics. I'd like to argue that catastrophic rock failure is a dragon king, which can be explained using this classic three-stage creep curve. But we know when a rock is subject to a constant load below its instantaneous strength, it will not fail directly but experience a progressive degradation over time. It will first exhibit a primary creep adjusting to the new stress state. Then it will enter the secondary creep phase associated with a roughly constant strain rate over a long period of time. Then up to a certain point, the rock will enter a tertiary creep phase where a catastrophic failure could happen if there is a positive feedback characterized by this M exponent in the Volk's law larger than 1. If there is no positive feedback corresponding to that this M exponent is smaller or equals to 1, the strain can still accelerate but no failure would occur. Clearly, catastrophic rock failure is a dragging king, which is born from the unique mechanism, which is the positive feedback process, and has a huge impact on the system, corresponding to the rupture of the entire rock sample. We can also see that when the rock approaches a failure, it will exhibit a phase transition from the secondary creep to a crisis, acceleration crisis. Different phases are governed by different processes as embodied in the different equations here. So we can expect the system exhibits different properties and responses. If we can detect this change in system responses and properties, we can predict catastrophic failure beforehand. Many landslides in the natural system exhibit similar strength degradation behavior over time. As you can see here, for the Priando landslide, it exhibits a long period of secondary creep before entering into an acceleration crisis in early May 2012, and this crisis ended with a catastrophic failure on 15th May 2012. If we plot the probability distribution of slope velocity data, we found that before this acceleration crisis, the velocity data nicely follow an inverse gamma distribution. Then during the crisis, a significant deviation from the inverse gamma distribution can be observed. This provides a possible way for us to predict this acceleration crisis and the catastrophic failure by detecting dragging kings. To achieve this, I developed a rigorous statistical tool to quantitatively detect dragging kings. First, I define a null hypothesis that all the velocities follow the same population. Then I use the Anderson-Darling metric to identify potential outliers and further conduct outward sequential test plus a block test to quantify the significance of these outliers by calculating the p-value under the norm. If the p-value is smaller than the significance level alpha, we can reject the norm, which means that the velocity data do not follow the same population, suggesting that the slope has transitioned into a crisis. If this is the case, I will then use a phase diagram to analyze whether the slope would evolve into a catastrophic or a slow landslide. I'd like to elaborate a little bit more about this phase diagram. According to the fundamental reduction theorem, a system under critical transition is usually governed by one or two or rarely three control parameters. However, it is not a trivial task to identify these control parameters for a complex system like landslide here. In our work, I managed to identify the two dimensionless parameters that govern landslide evolution during its transition to a crisis. One is the M parameter, which is the power law exponent in the Box law, as I already mentioned before, and it governs the nonlinearity of interactions in the system. The second parameter, omega, is a dimensionless parameter related to the heterogeneity or stochasticity of the system. The two parameters can beautifully define the boundaries between black swan, dragon king, and slow landslide, as you can see in the right side figure. Since the landslide in reality is an open system, which dynamically evolves over time, this phase diagram would also allow us to track the landslide evolution from a dynamic perspective, which I will also show in the next few slides. Now let's look at the prediction results of the Priando landslide. You can see that about 1 week to 10 days before the failure, there is a systematic decline of p-values, which clearly indicates that the slope has transitioned into a crisis. Then on the fifth diagram, we can also see these landslides evolved into the Dragon King regime. So you can see that by using my method, I could predict the failure of the Prianto landslide almost 1 week beforehand. I'd like to further test my method using 2 other landslide cases. This is the Vestlandet landslide in Norway, which was reactivated by permafrost thaw under the global warming. This landslide experienced significant deformations in the years of 2017 and 2018, but didn't collapse. It only failed in 2019 in September. The local authority adopted the conventional velocity threshold method to mitigate the risk, and they released 16 red alarms. Except for the last one, all the preceding 15 red alarms were found to be false alarms, which means that people were evacuated from the hazard zone, but no failure happened. If we plot the slope velocity distribution, we can see that the data also naturally follow an inverse gamma distribution. However, it's not so clear to see whether there is any deviation happening in the system during the crisis. Let's do the quantitative analysis. Here we can see that in the year of 2018, some radar points showed p-value drops, but only one radar point dropped below 0.1. We see the overall p-value dropped below 0.1 starting from November 2018, which indicates that the slope may have transitioned into a crisis. But when we look at the phase diagram, it is still in the slow landslide regime. It is only after the summer 2019 we see systematic p-value drops happening in the system, where more and more radar points show the p-value decline. And the overall p-value also starts to stay below 0.1. Especially, it is only in the last week before the failure, all the radar points showed the p-value responses, which indicates that the slope has globally transitioned into a crisis. When we look at the phase diagram, we can also realize that this landslide has evolved into the Dragon King catastrophic landslide regime. Compared to the velocity threshold method adopted by the Norwegian authority giving 15 false alarms, my approach can give 0 or maximally 1 false alarm if we adopt a majority rule when interpreting the p-value dynamics. Now let's look at another case, which is the Musflug landslide in Switzerland. This landslide was reactivated in response to the ongoing retreat of the Alash Glacier. It exhibited significant acceleration and deformations in late September 2016, but it didn't collapse. If we plot the velocity distribution, we can see a clear deviation of the velocity data from the inverse gamma distribution during the acceleration crisis. In the forecast analysis, we can see a systematic p-value decline in late September, which means that the slope has entered into a crisis indeed. On the phase diagram, we can see that this landslide was indeed in the Dragon King regime at the beginning of the crisis, but later evolved into a slow landslide. The deceleration of these landslides was actually later found to be due to the buttress of the viscous glacier at the toe of the slope. From these different test cases, I hope you would agree with me that real-time forecast of catastrophic landslides is possible. However, you may still question me about whether my method is generally applicable, why inverse gamma, why Dragon Kings. To answer this question, we need to understand the mechanisms behind this phenomenon. Recently, I have developed a stochastic dynamic model to simulate the landslide displacement time series by modeling the secondary creep using the Keston process, which can nicely capture the emergence of inverse gamma distribution. I also modeled the slope tertiary creep using a stochastic differential equation, which is the stochastic version of the Vogel's law, and it can nicely capture the emergence of dragging kings. These simulation results provide a very good mechanistic support to my forecast method. Now let's revisit the conventional methods. Why the velocity mass threshold method doesn't perform well? The reason is that the creep to crisis transition of a landslide is not determined by the point-wise velocity magnitude, but it should be determined by the full velocity distribution and its evolution. That explains why so many false alarms could be released by this conventional velocity threshold method. Now let's also revisit some of the previous time to failure analysis. We can now realize that these predictions are not physically justified because Vogel's law that governs the tertiary creep was used to fit the secondary creep phase. Of course, it won't give relevant predictions. So to conclude, I would say landslide failures can be predicted, but we need to know when and how to make a prediction. Equally important, we also need to know when to not try to make a prediction. This requires a sound understanding of the physics behind predictive laws. The research presented in this talk has been published in our two recent geophysical research letters in this year. And if you are interested, you can refer to our papers for more details. And having said this, I'm very happy to answer any questions. Thank you very much.